Returning to the emission spectra. So let's say we're going to look at hydrogen. Every hydrogen atom has identical orbits. So every hydrogen atom can undergo the same energy transitions. Okay, so let's say you have a hydrogen atom. And so you have the nucleus right in the middle. And because I don't have a lot of room to draw, I'm going to just draw like half of the orbital. So let's say this is n equals 1. This would be n equals 2, 3, 4, and 5. So just imagine this is one big circle, right? Now, if we have another hydrogen atom, it's going to look exactly the same. Okay, so this statement, when it says every hydrogen atom has identical orbits, every hydrogen atom can undergo the same energy transitions. So, however, since the distances between the orbits in an atom are not all the same, no two leaps in an atom will have the same energy. So, for example, if we went from n equals 2 to n equals 1, so we went from 2 to 1, what would we say about this energy? Would it give off very high energy or low? This would be very low energy. So the light that's produced when it goes from 2 to 1 gives a low energy. So a low energy, what kind of wavelength would that be considered? This would be a very high wavelength. Remember, because they're going to be opposite. A high energy, low wavelength. Now, let's say we went from n equals 5 to n equals 1. So the electron was in an excited state in the 5th orbit, and then it dropped down to the 1st orbit. When it drops down, it emits light, right? Okay, so we get to see some type of light. Now, this light will have a very high energy associated with it because it's going from a high excited state to a low excited state. So it's going to have higher energy than if it went from 2 to 1. So the higher the energy, the shorter the wavelength. Therefore, we're going to see different colors associated with these different transitions. So remember, energy is related to wavelength, and we've kind of already talked about this. The higher the energy, the shorter the wavelength, and the wavelength determines color. So if we went from 2 to 1, we will see a different color than if we went from 5 to 1. Therefore, we get an emission spectrum that has a lot of lines, or meaning wavelengths, that are unique to hydrogen. And these are all due to the electron transitions. Emission spectra of hydrogen. So we observe colors due to the electrons relaxing to a lower energy level. I want you to fill in the gaps here, and you're going to fill them in based off of the figure at the bottom of the slide. Continuing on with the line spectrum of hydrogen, scientists wanted to discover a pattern in the atomic spectra of hydrogen and other atoms. Now in 1885, a Swiss schoolteacher named Johann Balmer discovered the wavelength specific to hydrogen. So no matter what hydrogen they burned, hydrogen would always give off these wavelengths. So they would give off a red color, and that red color has a wavelength of 656 nanometers. Then you also have a green wavelength, which is 486 nanometers, a blue one, as well as a purple one. Okay, now let's look at these wavelengths here. When I'm looking at the different colors of the rainbow, we have red, orange, yellow, green, blue, and purple. Which one of these has the longest wavelength? This one would have the longest wavelength, and purple would have the shortest. Now you need to know that. You also need to know which one will have the higher energy. So which one does, red or purple? Purple will have the highest energy. Red will therefore have the lowest energy. So now let's look at this according to our spectrum of hydrogen. Going from n equals 3, what they will see is that when it goes down to its ground state, this will give off a very low energy. And the low energy will be associated with a very long wavelength, 656. Okay, now let's go up an energy level to n equals 4. Okay, so now it will drop even further down. So this will have like a higher energy in comparison, higher energy. And so therefore it will have a shorter wavelength. And that wavelength is green. Okay, so now you can do that all the way up to purple. So with purple, you have n equals 6, so it's at an extremely high excited state at the 6 energy, and it drops down to its ground state. Let's call it that, GS. So this gives off a ton of energy, like the highest energy. With the highest energy, it's going to have the shortest wavelength. And that shortest wavelength we see is purple. Now, once Johannes Balmer collected his data, through trial and error, he developed an empirical equation to predict the line spectra of hydrogen. What does empirical mean? Empirical means through observation. So he collected the data, he found the certain wavelengths that hydrogen produced when it was burned, and he came up with this equation. The equation is 1 over the wavelength is equal to R infinity, which is called the Rydberg's constant, times 1 over 2 squared minus 1 over n squared, where n is a greater number than 2. The other way you could write it is you could find the frequency. Now remember, the frequency is related to c over the wavelength. Okay, so what he did was, instead of having the wavelength in there, he just put frequency and accounted for this with a by multiplying it by the speed of light, c. Okay, so, and then they were also given the Rydberg's constant, which is 1.097 times 10 to the negative 2 inverse nanometers. Now at this time, he and the scientific community were unaware of orbitals having specific energies, right? So at that time, they had no idea about Niels Bohr. Niels Bohr, remember, came in 1919. That's when they looked at those specific energy levels. This, Johannes Balmer, was in 1885. Okay, now right now we know what N really means. N means these energy levels. But looking here, when he put N into that equation, he just said N had to be an integer. He had no idea about these energy levels. So isn't that super interesting? Now, however, this equation helped advance this notion that energy levels have specific energies by showing that only specific wavelengths were possible. Problem. Using Balmer's equation, prove the hydrogen spectra, and then for the energy levels of 3, 4, 5, and 6. Let's do the first one together. So we're going to say N is going to be equal to 3. The equation that I need to use is the Balmer equation, which would be 1 over wavelength is equal to the Rydberg's constant times 1 over 2 squared minus 1 over n squared. Now, they need us to show the different wavelengths we can get when we have n equals 3, n equals 4, and so forth. The first one we'll do is 3. So let's plug 3 in. Now the Rydberg's constant they give us, which was on the previous slide, and the units are inverse nanometers. You don't want to forget units. And then because our n is 3, we'll square it. 3 squared. Okay, now I'm going to multiply these numbers. And so I will get 1 over wavelength is equal to 1.52 times 10 to the negative 3 inverse nanometers. But I need to figure out what the wavelength equals. So how would I get wavelength by itself? Well, right now it's on bottom. We need to get it to the top. So I'm going to multiply both sides by wavelength. This allows me to cancel off the wavelength on the left side. Okay, now the wavelength, I still need to get it by itself, so now what must I do? Divide both sides by that number. 1.52 times 10 to the negative 3 inverse nanometers. This allows me to cancel off the number on the right side. So now, my wavelength will be 1 over 1.52 times 10 to the negative 3, and I will get 656 roughly. What unit will this have? Okay, here you have 1 over inverse nanometers. Through math, you bring the nanometers up to the top, so it is going to be simply nanometers. Okay, so at n equals 3, so when an electron is there and it goes down to this second energy level, it gives off a wavelength of 656 nanometers. Okay, now what you need to do is solve for the other 3. So you need to look at n equals 4, n equals 5, n equals 6. So go ahead and do that. You can always check your work by looking to see what you should end up with by looking at the line spectrum of hydrogen. Now Johannes Rydberg, this is where the Rydberg constant is coming from, this person. He adapted the Balmer equation to provide the entire spectrum of hydrogen instead of only the visible series. So the Balmer equation is only good for the visible light. Johannes Rydberg came up with an equation to take into account the ultraviolet light, infrared, and so on. So the entire electromagnetic spectrum. This equation is given here, or instead of having it 1 over wavelength, you could also figure out the frequency by taking into account the speed of light, which is c. Now, m and n has to be greater than m. And here n and m are integers. These are whole numbers. Let's look at a problem involving the Balmer-Rydberg equation. What are the 2 longest wavelength lines in the series of the hydrogen spectrum where m equals 1 and n is greater than 1? And we're given the equation for this. Okay, when we are looking for the longest wavelength, what does that correspond to energy-wise? Does that correspond to a large energy or a low energy? A long wavelength corresponds to a low energy. So you only want to drop down very little between the different energy levels. So if you have, let's say, here's your nucleus, m has to equal 1. When m equals 1, we're just saying that's the first energy level. Now, if it falls down a very short one, you want to do the next one, right? So you want to look at the second energy level. Let's say n equals 2. And then because you want to find 2 of them, you're going to go from 2 to 1, as well as from 3 to 1. So you have to find the wavelengths associated with both of these. I want you to go ahead and try this problem. We'll see if you're right when you get to class.